Okay, dear students, now let us move on to solving further numerical problems from engineering mechanics from solution 2.81, problem set 2.6. We have been using method of moments to solve numerical problems instead of doing method of projections. In problem set 2.5, we used to solve them by using method of projections. Means in 2.5, we used to find out a point about which and used to draw an axis, x-axis, y-axis. And there were forces like Q, some force to this side, some force to this side. And we are drawing the components. Component of F, component of S, and making them equal to Q, component of F along x-axis, component of S along x-axis, and making this equal to this to study equilibrium. But in problem set 2.6, we will not be considering the method of projections. Means we will not be finding out the different rectangular components of different forces involved at a particular point and apply sigma x is equal to 0, sigma y is equal to 0. That we shall not do in problem set 2.6. Rather, we will solve the same problems, similar problems by moment of a force. Now, that is the turning effect of a force about a given point. Means we will not be required to find out the angle in most of the cases. So now look at the statement of the problem, a rigid bar. This AB is a rigid bar, means with a small force you cannot deform it. The rigid bar AB is supported in a vertical plane. This bar AB is supported in a vertical plane. Means this is, suppose this is a wall. AD is a wall, the wall is like this, and the bar AB is supported, and the bar AB is supported not in a horizontal plane, in a vertical plane like this. And there is it plane and carries a load Q at its free end. The rigid bar AB is fixed here at A to this vertical support, and this free end B has a load Q hanging from it vertically downward. So Q is to the weight, Q is to this side. Neglecting the weight of the bar, the rigid bar AB is weightless. Compute the magnitude of the tensile force S induced in the horizontal string CD. Look, this is a string. So the bar AB, due to the load Q, will try to turn, will have a turning effect about the point A. The bar AB will have a turning effect, clockwise turning effect due to the load Q suspended from the free end B of the rigid bar AB. So this string CD, which is a string, the string will be tightened, means there will be a tension developed along the string CD. If you consider point C, that tensile force will be to this side. If you consider point D, it will be to this side. Let it be S. Now, we'll find out that how much is that. So, what is given? CD is a string. AB is a rigid bar. Its weight is not to be considered. It is given, it is weightless. So, just I explained how this tensile force, the tension force, acts in the string away from the point C to this side and away from the point D to this side. If you are considering point C, then the direction of the tensile force S in the string is to this side, and the direction of the same tensile force S, if you consider point D, is to this side. Now, considering point C, the tensile force is towards the left. The tension force, which is the tensile force in the string, acts away from the point C. Now, let E is equal to the point where the line of action of S and Q meet. I have redrawn the diagram. The line of action of this tensile force S in the string, if you produce it to this side, it will meet at here, and let this point is equal to E, which I have shown in a different diagram here. The tensile force S in the string, when produced, the line of action of S is produced to this side, and this is the line of action of Q. Both meet at point E. And there will be a third force. This S is one force, this Q is another force. There will be another force at point A, that is the reaction force. Let it be RA. So RA must also pass through the same point E. So RA also must pass through the same point E. Now, therefore, the RA, the reaction at A, must pass through E. No need to find angle because we are not considering method of projections. So there are three forces, S, Q and RA, tensile force, the load Q and the reaction force at A. Therefore, RA should pass through the point A, through the point, RA passes through the point E. It has to pass through the same point E. Now, now look at, so there are three forces, S, Q and the reaction force RA. If you consider this point as the moment center, means about which all these forces S, RA and Q will have some turning effect. But since RA is passing through this point, means RA, the line of action of RA passes through the point A, means RA does not have a perpendicular distance from point A. So RA will not produce any turning effect about the point A. So RA does not have any turning effect about point A. This S, the tensile force in the string, is at this perpendicular distance from A to F. A to F is the perpendicular distance of the line of action of this force S from the moment center. So this S will have a turning effect about point A. And how it will be that? It is force is to this side, this is the perpendicular distance, so it will try to rotate anticlockwise. Again, the line of action of Q, this line of action of Q from the point A is at this perpendicular distance from A to G, and from A to G is same thing as from F to E. So this load Q hanging from the free end of the rigid bar B will have a turning effect about point A, and how much will be that? Q times this perpendicular distance AG, and that will be clockwise. This turning effect, due to S, the turning effect about point A is anticlockwise. Due to Q, the turning effect about A is clockwise. And the rigid bar is in equilibrium, means it is neither rotating about point A nor it is translating, moving in a straight line. So since it is in equilibrium, the sum of the turning effects about point A should be 0. That is the understanding. So let us, so as I just explained, S has a perpendicular distance from A, that is equal to AF. Look at here, S has a perpendicular distance from A, that is equal to AF. Q has a perpendicular distance from A, that is equal to AG, that is same thing as FE. The line of action of Q is at this perpendicular distance from A to G, that is same thing as from F to E. So therefore both S and Q will have moment about point A, where A is the moment center. Therefore both S and Q will have some turning effect about the moment center A. And since the rod is in equilibrium, the sum of the moment about the point O should be 0. Means the clockwise movement should be equal and opposite to the anti-clockwise movement. And as we have discussed in previous lessons, the moment of a force is nothing but the product of the force and the perpendicular distance. Product of the force and the corresponding perpendicular distance. And the force S, the tensile force S, has a perpendicular distance AF. The tensile force S has a perpendicular distance AF, due to which the turning effect is anticlockwise. And Q, the load Q, has a turning effect Q times AG, where AG is the perpendicular distance. Look, AG is the perpendicular distance from the line of action of Q of the point A. So Q times AZ is a clockwise movement. So if both are equal, then it will be in equilibrium, and since it is in equilibrium, therefore they are both are equal. Now look at the triangle ABC. Look at the triangle ABC. Look at the triangle ABG. From A to B is given as L. A to C is L by 2, C to B is L by 2, as given in the book. From here to here is L by 2, from here to here is L by 2, therefore from A to B is equal to L. So in triangle ABC, if you take sine alpha, it will be AG over AB, and if you cross multiply, you get AG as L sine alpha. AB is L, this angle is alpha. By cross multiplying, you get AG is L sine alpha. Now similarly in triangle AFC, now let us look at triangle AFC. Now triangle AFC, this angle is alpha, and this hypotenuse from A to C, because this is 90 degree, from A to C is L by 2. So to find the perpendicular distance AF, if I take cosine of this angle, cos of alpha will be base over hypotenuse, that is AF over AC. And if you cross multiply, in triangle AFC, AC is L by 2, CAF is alpha. So if you take cos alpha and cross multiply, you get AF as L by 2 cos alpha, the hypotenuse times cos alpha. So AZ is known, AF is known. Now put these two values of AF and AZ here in equation 1, then it is solved. So then it is solved. S remains as S. For AF, I write L by 2 cos alpha, L by 2 cos alpha equal to Q AG, which I just found out from the triangle ABG, L sin alpha. For AG, I put L sin alpha. So now LL cancels because both are multiplied on either side. Now, so take 2 to this side. This was in the denominator, so this will come to the cos alpha by 2, Q sin alpha. 2 comes to the numerator here. Cos alpha comes to the denominator here, is divided. Sin alpha over cos alpha is equal to tan alpha. So 2Q times tan alpha is your S. That is the tensile force developed in the string. In the string CD, which is holding this bar AB from turning about the point A. This bar AB, due to the load Q, should try to turn about this point A. So this tensile force is holding it back from turning, and thus S comes out to be 2Q times tan alpha. 2 times the load times the tan alpha. So that is what is all about. So I think things are becoming interesting now, and you must be finding engineering mechanics pretty easy now. If you think it is useful for you, please do forward it and give me your comments, and how things can be improved, you can let me know. And if you like, you can pass on to your friends also. Thank you.